morning, ma'am. I am Rucha Gandhi, and the topic of my today's presentation is Terahertz Electronics. So, listening to the topic, first question what would struck in your head would be, what is Terahertz Electronics? So, let's have a look on it. Terahertz Electronics refers to the study and development of electronic and photonic devices that operate in terahertz frequency range, typically between 0.1 terahertz and 10 terahertz. This region lies between, of course, microwave and infrared light in the electromagnetic spectrum. So, this region bridges the gap between microwave and infrared technology, also often called the terahertz gap, because traditionally electronics and optics struggle to efficiently generate and detect terahertz waves. Terahertz waves have non-ionization radiation, making them safe for biological application. Terahertz signals experiences high atmospheric absorption, limiting long-distance propagation. So, as we are Gen Z generation and before knowing about its history and whatnot, we just want to know about its importance. So, let's have a look on the importance of terahertz electronics. Terahertz electronics is crucial because it enables a wide range of advanced applications that are difficult or impossible with conventional microwave or optical technologies. Its importance lies for like high-speed wireless communication, medical imaging and healthcare, security and defense, non-destructive testing, space and astronomy, scientific research and material analysis. So now let's have a look on the history of terahertz electronics. Let's go from the very basic, from the 19th to 20th century. Of course, Maxwell, the we can say laid the groundwork for electromagnetic wave theory. Hertz, of course, we all know him very well, experimentally confirmed electromagnetic waves through terahertz range remain unexplored. J.C. Bose conducted early experiments in millimeter waves close to the terahertz ranges. Now, our next is what were the first attempts and challenges. Initial research faced difficulties due to the terahertz gap. Development of Scotty diodes, free electron lasers, and photoconductive antennas improved terahertz wave generation. So, what were its breakthroughs and modern advances? Quantum cascade lasers and graphene-based devices revolutionized terahertz sources development. 6G research fueled interest in terahertz communication for ultra-fast wireless network. Advancement in CSMOS and plasmonic terahertz detectors made terahertz electronics more practical for real-world application. Now, what are the sources and detectors for terahertz? These sources were for the first when it was okay. These sources are electronic terahertz sources, Scotty diodes, gun diodes, and impact diodes. These three diodes were used early. Now let's just have a small look at what is Scotty diodes, gun diodes, and impact diodes. So Scotty diode, semiconductor diode with a low forward voltage drop used in terahertz mixtures and detectors. Let's just have a look on it. This is Scotty diode, discovered by German physicist Walter H. Scotty. Is a special type of diode in which P layer is replaced by metal layer. Our next source is gun diode. A gun diode is a semiconductor device that operates using the gun effect where it exhibits negative resistance to generate high frequency microwaves, making it essential for like radar and communication systems. Just have a look on it also. This is what a gun diode look like. Now, our next is impact diode. An impact diode generates microwaves using Lagrangian multiplication and transmit time effect, suitable for high frequency application. Let's have a look on what is an impact diode look like. This is what an impact diode look like. So now let's move further to its fundamental concept. So there I have divided into 2 or 3 parts. Electromagnetic spectrum and terahertz region. I know this is very basic, but let's have a small look on it. Next is generation and detection of terahertz. Next is propagation characteristics. So first is electromagnetic spectrum and terahertz region. The electromagnetic spectrum consists of different types of waves categorized based on the frequency and wavelength. The terahertz region lies between the microwave and infrared regions, typically in the range of 0.1 terahertz to 10 terahertz, as we talked before. Here is a small picture of what electromagnetic spectrum looks like. So our next fundamental concept is generation and detection of terahertz waves. There are two types of approaches, electronic approaches and photonic approaches. In electronic approaches, we have Scotty diodes and Gunn diodes used in multipliers to generate terahertz signals, while in photonic approach, we have photomixing, difference frequency generation, DFG, use two infrared lasers to create terahertz waves. And on the next side, another side, we have resonant tunnel diode, that is RTD, compact solid state source for continuous wave terahertz generation. And on photonic side, we have quantum cascade lasers, high power terahertz sources based on intersubstant transition in quantum Ball. On the electronic side, we have next terahertz transistors like SISMOS, gas-based, enable integration for of terahertz circuit. While on photonic, we have optical rectification and terahertz time domain spectroscopy. Uses ultra-fast lasers to generate breadbone terahertz pulses. Backward wave oscillators and impact diodes. High power sources. And on the photonic side, we have free electron lasers, terahertz radiation sources for research application. So now what is photonic terahertz sources? Photonic terahertz sources generate radiation in the 0.1 to 0.10 terahertz range and are used in spectroscopy, imaging, and communication. Key types include quantum cascade lasers, photoconductive antennas, and non-linear optical techniques. They offer high bandwidth and precision, making them vital for application and non-invasive imaging, molecular analysis, and ultra-fast communication. So, what are the other sources of terahertz and what are the detectors? So, as we look about only three sources and detectors, I have some other sources and detectors. Let's just have a small look on it. Terahertz detectors and imaging. Bolometer, Scotty diode detector, FET based detectors. Terahertz wave guides and components used for filters, antennas, and amplifiers. And now, of course, recent advance in terahertz source development. Now, what are the applications of terahertz electronics? Terahertz electronics is used for like wireless communication, high speed 6G and beyond. It is also used for security and imaging, like in airport sensing, concealed object detection. In medical and biological applications, it is used like in cancer detection and non-invasive imaging. It is also used in industrial and scientific uses like non-destructive testing and material characterization. Of course, in space and astronomy, cosmic background radiation study, and in, of course, military and defense as a radar and a very super fast communication system. Now, what are the challenges and future prospects? So let's have a look on challenges. Technical challenges like power limitation, material constraints, high attention. Next, we have manufacturing and cost issues. Of course, cost issues is a big challenge for our country, but we slowly and gradually we are overcoming it. So just have a look on it. Also, fabrication complexity, integration with existing tech, standardization and regulation, frequency spectrum allocation and safety, emerging trends and future risks, Griffin-based terahertz devices, meta surfaces, AI in terahertz. Now, we have seen the challenges, but what are its future aspects, or I can say prospects? I have prepared a small roadmap for it. Let's have a look at it. So this is a vision. This is a vision for like 2040, and there are many things. Some points that I have discussed also, like information and communication security, biological and medical, industries, environment and space and whatnot. But nowadays it is on a slow pace, but till 2040 it would be like on the verge of it. So let's have a small look what we have or what I have discussed in my whole terahertz section. Terahertz Electronics bridges the gap between microwave and infrared frequencies, opening up new possibilities in communication, imagining, and sensing. Early theoretical foundations were laid by like James Clerk Maxwell, Hertz, and J.C. Bose. Significant progresses faced initial challenges due to the terahertz gap, but breakthroughs in Scotty diodes, free electron lasers, and photoconductive antennas propelled research forward. Modern advancements include like quantum cascade lasers, graphene-based devices, and CSMOS and plasmonic terahertz detectors, making terahertz electronics more practical and versatile. So, at last but not the least, let's have some acknowledgement for our great scientists like Maxwell, dynamic theory of the electromagnetic field. Next is Hertz experiments on the generation of electromagnetic waves. Though it was not for the terahertz waves, but at least he had started something. Next is J.C. Bose early experiments in millimeter waves. Next is recent searches like articles and papers on quantum cascade lasers, graphene-based devices, CSMOS, plasmic terahertz detectors, and whatnot. And of course, 6G research innovatives, contribution for various academic and industry research. And this was all about my terahertz electronics. Thank you, ma'am.